Hi, everyone. Welcome to the second webinar in our community education series. Today, Harshad is going to talk about Word2Vec, and this is a follow-up from the webinar a month ago, which was around neural networks. We will keep coming up with these webinars, and if you are interested in participating in them, just let us know through our website, LinkedIn, or various social media forums. All right, Harshad, all up to you now.
Okay. Hello, everyone. As Praful mentioned, I am Harshad, and we will be discussing word embeddings today. And the idea of the webinar is not to go in technical details, but to follow up on why this came up or what was the intuition behind word embeddings and how they can be used in practice. If you are familiar with natural language processing, word to vector, you must have already heard of this as a term that is used in almost all of the newer NLP techniques. So let us start. So first, let me present a plan of what we are going to do for the next 30 minutes or so. We will start off with discussing why word embeddings are necessary. We will define the problem and what is the ideal solution to the problem. Then we will discuss some common word representation approaches. Following it up with word to vector, we will go in detail with how word to vector was, what was the intuition behind word to vector, how it was implemented, and what were the results. Then we will follow that up with Glove, which is another kind of vector representation of words. And in the later part, we will cover some how practically word vectors can be coded. And a spoiler alert here is that it is very easy to code word vectors. And what are the design considerations when you start using word to vector in one of your projects. Finally, we will conclude with how we are using word vectors at Coseer and what more we can do with word vectors. So first, so we will try to define why we need word vectors. We as humans use language extensively, even in text. Like this presentation is coming to you via text, and my voice, of course, but you can read the text on the screen. And we as humans also perform so many activities around this text. Search, classify those texts. We can translate the text. And more importantly, we can understand and react to the text. So the text also comes to us in many forms like documents or tweets or Facebook posts and several other things, right? But so we as humans are very natural in doing this. But can a computer understand text? So the answer is no, of course. So computers don't understand text as is. Because computers only work with numbers or not even numbers, bits. So strings don't on their own, they don't hold any explicit information about the meaning of the word. For example, if you get a string like cat, it is, for a computer, it is just a stream of characters, or in fact just ASCII code representations of those characters, and you don't actually get anything, any meaning out of those strings. But as humans, if you see a string of characters like pizza, and then you see a string of characters like pasta, you inherently know that these two are somehow related to food. But and also with pizza, you can also relate it to Italy in some way. And so is it possible for us, for computers, to do this? And that is the problem that we are thinking about now as a community of AI developers. This is where we are. That this is the problem that we want to solve. And the solution, a proposed solution, is some of these tasks can be made made easy by doing a numerical representation of words. And this representation is essentially at a much higher level than ASCII representations. Uh, and with this representation, what we are trying to achieve is that the meaning is captured in some way, and that meaning is then becomes computable, as computer scientists would say. It is essentially we can perform computations on top of these relationships or representations, and then figure out relationships between the words or context where the word is being used. And so this representation makes the computation very easy, and that is why we want to find a way of representing those words. And what is an ideal representation is the next question. That if we can define what is an ideal way to represent, we could essentially look at various representations and figure out which is the best one to use. So there are 3 points here. The first one is that it should be compact, because language is such a fluid and huge amount of data is part of language. If each word representation becomes a large vector or a large data, it cannot scale up to for us to process all of the words. So the vector representation, or the representation that we are creating for the word, should be a compact representation. The second is it should have some cognitive significance. So they should be the meaning, words that mean the same or are similar in structure need to be closer in that space, or if there should be some way of saying that these words are similar looking at their representations alone. And with that comes the strength of AI, where we can use, if it is possible for us to use those representations in a semantic way, we can use AI to build on top of those representations and do much higher level tasks like understanding or even making intelligent bots out of that. So that is the second point that is an ideal representation would have. And the third ideal point of representation is that it should be easy enough to combine those representations to form documents. And this is significant in the sense that words alone don't mean anything, and they always have to come as a part of a sentence and those sentences come as part of paragraphs, and those paragraphs then come as part of documents. So if we have a good enough representation of the word, but we cannot combine 2 of those words together or 4 of those words together to form a phrase, that representation cannot be scaled up for the computer to understand the entire text that we are looking at. So that is the ideal representation that we have. And so we'll look at some of the common representations that have already been used before word to vector, and then see what are their problems, and then go on to word to vector. So the first one that is well known is WordNet. And WordNet is essentially a graph of words as nodes and their relationships as edges. And these relationships are handcrafted by linguists. So the relationships are like synonym or hypernym or hyponym, if you guys are familiar with those. Essentially, synonyms is at the same level, whereas hyponym is a much higher class of the one that is. So, for example, a vehicle is a hypernym of car, and similarly, vice versa for an hyponym. But these relationships are not easily understood. But and so even if we have these relationships with us as a part of the WordNet package, to construct a graph out of that and to understand a sentence using these relationships needs linguistic knowledge. It is not possible to directly, so we need to write rules for the computer to understand that these synonyms or these hypernym relations then turn out to be, in the end, this is the final conclusion of that sentence. Another problem with WordNet is that it is not trainable. So it is stuck in the past. Whenever it was first hand coded, it is still there. And as language evolves, WordNet has not evolved with the language, so we are missing out on various opportunities. Another problem with WordNet is that uh, it doesn't have vague relationships or other relationships other than the linguistic ones that are hard coded. For example, um, for a president of a country or a prime minister of a country is not a relationship in the WordNet, but for a person or a computer to understand a text, these relationships are very important. So those are some problems with the WordNet. The second common representation, or a very naive, easy representation that we have, is one-hot vectors. Essentially, consider we have a text which has a vocabulary length v. So there are v different words in the text. So to represent each of those words, we create a bit vector of the length v with only one of the bits as on. So the bit represents the word, and the rest of the bits are turned off. So essentially, combining these these one-hot vectors is easy to create a document. This is very basic representation, but it doesn't have any cognitive knowledge of the words. It is just basically a list of it's a list of vectors, and they don't relate to each other in any way. Uh, Another problem with this is the vocabulary length can go very high, and then representing each of the word with that vocabulary length is kind of very difficult and not sustainable to use in live systems. So we can see that both these representations, though have a lot of strengths, they all deviate from our ideal goal in some way. So we need to figure out to find a better solution to this problem. And uh, the thing that the word to vector guys did was they just made the computer learn on its own, learn the representation on its own. So whenever we say learning, the computer learning, we go to machine learning, and supervised learning is the easiest way to teach a computer. So what does supervised learning mean is that it takes in a data which is essentially knows what is the input and what is the output, expected output of a certain function, and it learns that what that function should be on its own. But in case of word representations, we have no such data available. We cannot handcraft such things for, say, 100,000 tokens or 100,000 words together. These hard coding, handcrafting these things is not easy. So getting tag data is almost impossible in that case. So the solution is to change the perspective and switch to untagged data. So text data is very easily available with the news corpus, or even Wikipedia dumps are very easily downloadable. So we can easily take untagged data, but from untagged data, we want to design still want to go to with a supervised machine learning algorithms because they work really well in the restricted settings that they have. So they designed a supervised machine learning problem out of the untagged data, which is fill in the blank. So let us consider that we have a long text input, and we put out a window of 5 words on top of that text, which starts from WT minus 2 and ends at WT plus 2, with WT being the central word. And we formalize this problem as a fill in the blank. in such a way that given the previous two words and the next two words, can we predict what is the word in between? Uh, but computer doesn't understand words again. So how do we input this word? So the one hot vectors that we discussed before comes to our rescue here. So we essentially represent this word as a one hot vector. This word as its own one hot vector. Yeah, let us consider that we have a long stream of text available with us, as we discussed, maybe from Wikipedia, maybe from Google News. And what we do is we put out a window of 5 words on top of that text. So it starts at WT minus 2 and ends at WT plus 2. And we formalize this problem as a fill in the blank for WT. So given that given the previous two and the next two words, can we predict what is the word in between? But again, the problem is that computer doesn't even understand WT minus 2 and WT minus 1. So we go back to our one hot vector representation that we had seen earlier. And so essentially we convert WT minus 2 to its own one hot vector and WT minus 1 to its own one hot vector. And because of these one hot vectors, we predict what is the one hot vector of the word in between. And as these one hot vectors have a one-to-one mapping to the word, we can then go back and see what is the word that is being that is predicted by the machine. So essentially, this is very easy to see that this is a supervised problem because we also know what is what is the correct output here. What is the expected output for this window is known. So we can then train our machine to predict that correctly. So essentially, what is used for the machine learning algorithm that is used in here is neural networks. This was what they did when they started doing Word2Vec. So this is essentially, it was also previously called a neural representation of words, which comes from this neural network. We will not discuss the neural networks code or neural networks working a lot, but essentially this is essentially how we combine the context words. These are the context words that go as an input to the neural network, and the predicted output is the output. The neural network here is a 2-layer neural network, and so we pass in the input to the first layer, and the second layer then predicts the output for us. Essentially, these layers don't do magic. They are just matrices and dot products inside them, but we'll get to that. So let's say we want to find so one of the hyperparameters to Word2Vector is n, the size of or the dimensions of the word vector that we want. So let's say it is capital N, and that is what we expect the dimension of our word embedding at the end should be. So the context words are passed as an input to the layer 1, which has a dot product with a v by n matrix W1, which is a layer 1 weight matrix. It creates a vector of 1 by n. This 1 by n vector is passed to layer 2, which again has a dot product with n by v matrix. There is a typo here. It should be an n by v matrix W2, and it creates a 1 by v vector again. And 1 by v is essentially, as we know, one hot vector kind of representation of the output. And this can be easily transformed into WT to predict the word. So this is the core logic of how this network works. Let us go to how it is trained. So this is it is not very difficult to train a neural network. Neural network training is essentially determining the values of W1 and W2 and minimize the errors in prediction. by the way, I am glossing over minor details in the neural network, like the bias and the number of neurons in the network, but it is essentially this, that we want to determine the values of W1 and W2 matrices. And that is what is training a machine learning algorithm is all about. So the algorithm is the basic algorithm is called back propagation, but I have tried to describe it in English here. What we do is we initialize it randomly, and for each window of 5 words in the text, so there will be thousands of, as large as our corpus is, there will be thousands of such windows. We predict what is the output vector, and we also know what is the expected output here. We compute an error between those expected and the predicted output. That error is propagated backwards in the network to modify the W1 and W2, and this can go on till we see that the error is reduced to 0, or maybe a very small value which we can ignore as an error. So essentially, when this network is completely trained, it can be used to predict the missing word in any given window, or in fact, it is even ready to face output of. So essentially, it is ready to face unseen data as well. So if we put in a new window of four context words and an unseen word, it can predict that as well. So so once the training is complete, we can. One more interesting thing is, where is exactly the representation that we are talking about? Where is the embedding? So essentially, this 1 to n vector is the embedding. So after the neural network is trained completely, that the value of trained matrix W1 is finalized for the given supervised data, we can use that layer 1 matrix or W1 matrix to predict, given any one hot vector, we can predict a 1 into n vector from that. A point to note here is that where the vocabulary is in the scale of 100,000s, the value of n is around 300 or 600 is the maximum that I have seen in the literature, or maybe somewhere in that range. So we are basically saying we can condense down a vector of 1 v, that is 1 into essentially what we are doing here is we are passing in one hot vector of an input word to the layer 1 of the of the trained neural network, and we get a hidden representation of 1 by n vector. So what is happening inside is just a pure mathematical dot product between this vector and the trained matrix. The intuition behind why this is a representation comes from the next layer. The next layer essentially converts this vector back to a one hot vector and gives us a prediction. So once the network is completely trained, what we want is to convert this one hot vector into a 1 by n vector, because that is the hidden representation. The size of this one hot vector is very large. It is kind of in the scale of 100,000, but the value of n is around 300 to 600. So essentially what we are doing is we are compressing or the information contained in the one hot vector to form a 1 by n vector, which has all the information of the word, but the representation is much smaller. Because one hot vectors were very sparse, this representation is very helpful. But what are we gaining by doing that is the most important question, I think. And so the most important thing is that it is kind of like a vector space model. So what we can do is we can just query the model for all the words in the vocabulary and save out a map of all the words and their vectors, and then just use those vectors too. So it is essentially like plotting the words in a space of 300 dimensions, and using those using those relationships between the locations of those words and figuring out things. The advantage of doing vectors is that it gives us vector arithmetic. So if we can say, if we can directly calculate how far away two words are in vector space, we are basically saying how far are they semantically, or syntactically, how far are they. And that is a huge advantage to have, because this becomes the computation of similarity then becomes very quick. The second thing is, how do two vectors relate to each other? For example, if two words lie in the same zone of the graph, or in the same area of the graph, they may be similarly related, or they may have some connection which can be determined by the word vector algorithm. And we can also extrapolate known relationships to find out other relationships. And a good example for that is here, where a vector for Japan minus the vector for sushi plus a vector for USA gives out a vector of pizza. And this is not made up. This is what they have in the paper as well. So these are some of the results from the actual literature of Word2Vec. I think I forgot to mention, this was developed by Mikolov when he was at Google in 2013. So it is 5 years old, and it has grown so much that it is now used in all NLP applications. This is like the standard starting point. Another interesting result from this was how do you find a word which has a similar sense to small as big is related to biggest. And they could also do like vector of biggest minus vector of big plus vector of small gives vector of smallest. And again, this is a result that they have shared. One of the more famous results, or whenever you Google say Word2Vec, the first result or first interesting result that comes up is always the vector of a king minus the vector of a man plus a vector of a woman, or gives out a vector of a queen, which was kind of surprising. And let us take a moment to realize that these things have not been taught to the computer. It has learned on its own, just looking at text data. So they had used a Google News corpus which had around 6 billion tokens, but so there is no human intervention needed for the computer to learn these relationships. For example, Einstein minus scientist plus Picasso gives a painter. To learn this using a hand-coded or a rule-based technique is almost is not imaginable to learn all of these relationships, but Word2Vector can learn that, and that is the power of Word2Vector. Moving on to another representation. So there's another representation of words called GLOVE. It stands for global vectors. And so the intuition behind GLOVE was that while Word2Vec only used a local window of 5 words, the people at Stanford University thought that they should also leverage a larger global context of where the word is. So they created a huge global matrix of co-occurrences. Essentially, the matrix has whenever a word occurs with another word, there is a count added to the matrix. And from that co-occurrence matrix, they calculated the probabilities of that word occurring in this context. And so essentially the key difference is that the GLOVE being probabilistic, it is a count-based method, whereas Word2Vector is a predictive neural network method. And one of the major disadvantages is that the huge co-occurrence matrix has to be created while training, but that is a one-time operation. So that people have been using GLOVE as well as Word2Vec, and it has been very successful as well. in the analogy tasks that they used it for. Moving on to coding the word to vector. So as we have discussed the neural network itself is not very difficult to code because it is just a two-layer network, and so it is very easy to write those dot products of those matrices and train that network on our own. But now all languages have adopted Word2Vec as a standard thing. Java has deep learning for J, Python has TensorFlow, and GenSim as well. GenSim is a very interesting library from Python in Python, which essentially has a lot more than Word2Vec, but Word2Vec in application is very easy in GenSim. It's like a 3-line code. And Glove has a open source implementation from Stanford. I think it is in C++. So essentially, if you want to include it in any project, Word2Vector coding is not the problem or not the point of consideration. What we want to consider is do we have enough data? So to get interesting results, Word2Vector needs a lot of data to train, because it is a predictive model, it is a supervised learning model, it requires a lot, and the input is essentially 1 by b vectors. So it requires a lot of data to train. And the second point is, though Word2Vector predicts words that are closer, or it has a distance metric which can be used to determine, because it is in the vector space, it can be used to determine which words are close together. But it is not for precise tasks like synonymy detection, or in fact, we cannot actually label any relationships in the same in the vector space like we did for WordNet. And that can be a problem if we have systems that depend on those relationships, or in fact want to exploit those relationships. Word2Vector will give you a more generic similarity or closeness metric to play with, but it will not give precise synonyms or relationships. The third point is, it is heavy computation is required to build those models. Though there have been many optimizations, it still requires GPU training to actually for a real world system to be trained. It requires a lot of time as well as CPU utilization. And one of the most important drawbacks of Word2Vector are it doesn't handle out of vocabulary words. So essentially, because the input and output is always one hot vectors, it is limited by what the vocabulary was when we started training the model. So we have to pre-compute what the vocabulary is going to be used and then use it to train the model. And this is a problem because in a niche domain-specific corpus, it is going to be very small, and we cannot add more data to it or use the new, in fact retrain any models that have been trained previously, because we cannot add in the vocabulary from these niche domains. So that is one of the biggest considerations when using Word2Vector. Moving on, these are some of the interesting takes on Word2Vector, or some modifications people have done over the years to Word2Vec. Though Word2Vec and Glove are the most basic, they are still used primarily for all the tasks, but people tend to modify them to fit their own tasks. For example, I'll mention a few of them and what are the differences that people have made. So fast text by Facebook is the, I think, the most important derivation of Word2Vec. in an interesting change, what they do is they also use subword engrams. So essentially, at a character level, they do engrams of the characters, so that they could model spelling variations. And as we can see, because it is Facebook, they tend to have a lot of spelling variations and spelling mistakes. And to not fall for those, they have modeled it as a character level engram as well. So not only words, they go to a character level and pick up engrams from that. Another variation is sense to vec, which essentially attaches a part of speech or a named entity tag to the word or a phrase, so that the querying becomes more accurate. So that we can, when we are training, we know that this is a noun, and that is what that is the context it appears in as a noun. And if something appears as an adjective, this is the context that it appears in as an adjective. And when querying, if we ask for an adjective, it will only, so the vectors will essentially also have the knowledge of that when they are trained. And the third most interesting one is talk to vec, which is essentially it tries to combine the word to vec training to form an internal representation of the entire document. And this was again developed by Nikolov after the word to vec paper. And what they do is essentially add another input while training, which holds the representation of the document. And whenever they train, they essentially that representation also gets trained with all of the possible windows inside that document. So these are these are not the only ones. There are a lot more, but these were the ones that I found interesting. Moving on to how we can use word to vec at Coseer. There are three things here. The first one is essentially the most naive or the most basic implementation, is that we can train our own model. We have text data, we can run word to vector models, train the model, save the model, and use that model or use the distance matrix from that model to figure out how we can train, so figure out all the relationships between the words. But this is a huge caveat here, that it needs large amount of data, and which might not always be possible for us. The second way to do it is using pre-trained data. So all the companies or all the people who work with word to vec or Glove or fast text, they have put out large vector models that they have trained on, so say Google News corpus of 6 billion tokens and Wikipedia corpus. So essentially what we have is a pre-trained model of vectors. So we have a vector space model that is essentially a general English model, and we can use that to at least leverage for the general English case, and then build on top of that the other synonyms that we want to figure out. Second one, the third option that I was thinking about was to bootstrap a word to vector model, and so a word to vector pre-trained model. So take whatever was already trained on English, and then pass on the new corpus or new smaller corpus that we have, and then bootstrap it and continue the training as it goes, and finally we will have a good representation of all the corpus words as well. I have been playing around with this idea for a bit. I have not yet successfully done this, but it seems to be possible to start training on our own and use a newer data set afterwards. But directly using a pre-trained model, I don't think it is technical challenge and not a conceptual challenge. So there should be some way, and we can figure that out. Yeah, that's it for the presentation. Are there any more questions?
Thanks, Arshad. A lot of questions are piping through the chat. So let me try and kind of moderate a few of them and ask a couple. So first of all, thank you. I think this is very revealing in terms of what's going on in the word-to-vector space. The first set of questions is actually to your last point, which is how we are trying to use it at Coseer or in general. You go from an academic world where typically there's a lot of data to practice with to a real enterprise world where the data, particularly if labeled clean data, is usually a scarcity. It creates a problem. So in your research, have you figured out who is using today Word2Vec very effectively in a real enterprise setting, not an academic setting?
The most important people are Google, because they essentially all their search algorithms also now bootstrap with Word2Vectors, and of course those being the core of their bread and butter, they don't reveal how they use it. But because Word2Vector came from Google itself, what they do essentially is, because they have access to a lot of data, they have trained models across domains, specific domains. And then I have read that the info box that comes up whenever whenever you search something on Google, the box on the side that comes up, that is completely triggered by Word2Vec. And though I don't have exact reference of how they've used it, but the point of using this in an enterprise application is always, of course, as we all have agreed, that academics work is very lab conditioned work, so it never works directly in any enterprise setting. But the point being, just like WordNet, we use WordNet or we use a resource to start as a starting point, and then move on further with whatever we get from that resource, and then write out our own models on top of that. So for example, we can treat Word2Vector or a vector space model as a thing that gives us words that are similar in some sense or are related in some sense, and then maybe we figure out how to use that similarity, or use only a top n similarity, and use that further to find out synonyms, or maybe for even for search applications, because those words are similar and they tend to occur together. We might be saying that, yeah, this is an interesting result as well, because even though it doesn't have the exact search term, it is still an interesting result in some sense.
So what I heard you say is that, I mean, Google, Apple, and Facebook are obviously different beasts. They have a lot of data, they have a lot of resources. But in a real enterprise setting, sounds like you're saying that Word2Vector could be an effective way to get started, getting more signals, or kind of get a baseline model and then improve upon it based on proprietary algorithms.
Yes.
Got it.
Exactly.
And let's turn a bit technical here. The V and N, and if I remember correctly, it's the number of things in the dimension of the matrix and the window size, right? I mean,
Yes.
What's an effective way to choose them? I mean, should we use 5 and 10 or 500 and 10,000? Like, what's a good way to choose them?
So these are hyperparameters and they need training. So it is essentially trial and error, and but it is essentially like running another neural network on top of this, which changes the values of these. And figures out what is the best possible value of from the output of the final error. So
I see.
essentially, V is something that we cannot modify. It is the vocabulary, so it is always the same. N is a choice that we make. So too small a n is going to have a lossy data, and too large a n is essentially losing out on why we are doing this. We want it to be a compact representation. So for now, of course, Mikolov, when they published the paper, they had a, a thing n ranging from 100 to 700 or something. So they did try, like at every 50 points, they did try out all those things. And I think 300 was the best results that they got on the Google News data.
Got it.
But they essentially tried out a bunch of things, and that's the way they did it.
So we are coming up on the time, so I'll just put in one fun questions. Now, Alexa, Siri, Cortana, chatbots, how are they or can they use Word2Vec?
Yes. So essentially now the point of Word2Vec is always finding similarities, right? So when you say, I will not say okay Google because my Google Assistant will start off. Hey Siri, and ask her about the weather tomorrow, and you say, is it going to be very hot tomorrow? She understands hot because she has been coded in that way. But if you use a word that is not exactly in the rules that she uses, then she might not answer correctly, and then she's going to say, sorry, I don't understand. But with Word2Vec, we know that, okay, with a vector space model, we know that hot is surrounded by humid or temperate. I don't know. There are other words in the weather region, right? So, or cold is, in fact, cold is also one of the close words to hot as well, because it's a synonym, but it still appears in the same context. So all these things, the similarity of a word is going to be helpful for her to understand, for the computer to understand what we are asking, right? So essentially, whenever we hit a text, it is always good to have more context of what that word means. And Word2Vector gives you exactly that this word is used in these contexts.
Got it. Makes sense. Harshad, thank you so much. And for the audience as well, thanks for participating.
Thanks a lot, guys.
And we are coming to an end of this. Again, please keep tuned to the series of webinars we are printing out about artificial intelligence, machine learning, cognitive computing. As we said, we started with neural networks, and now we are doing Word2Vec today, and there's much more coming up in the coming times. Thank you so much.